Hello, and this is the last section of section 9.7, and we're going to look at solving exponential growth problems. So this is the second type of application that I want to take a look at. Now let's take a look at the formula for exponential growth. This formula should look a little bit familiar to you, except that there's just a few different letters in it. You might notice that it looks an awful lot like the PERT formula, or the continuous compound interest formula we looked at in the last video. The difference is instead of A we have Y, instead of P we have Y sub 0. We still have the base of E, and now instead of R we have K times T. So let's take a look at what all those represent, and they are similar to what they represented in the last problems we looked at. K now, instead of an interest rate, is considered is a constant that represents the growth rate. So it often is a percent that's been converted into a decimal, much like the interest rate in the compound interest problems. The Y sub 0 is just a way we often represent what we call the initial population. That's similar to what we looked at as principal in the money problems. So the initial population is what did we start out with? And we call it a population because often we use these problems when dealing with sizes of different kinds of populations. The Y is going to represent the population after a certain time t. So notice Y is behaving just like A did before, and t is the time. But please note that this is not necessarily in years. So when you leave the money problems behind and you look at this in its more general form, you are actually going to be looking at time being any length of time. It could be seconds, hours, days, years, weeks, months. Any of those could be used here. So you need to pay attention to your labeling. So let's look at an example here, and this one should look a little bit familiar. You've actually looked at a few of these before. The size of the deer population at a national park increases at the rate of 3.3% per year. If the size of the current population is 124, find how many deer there should be in 6 years. Now this one is not quite as complete as you may have seen before. So we have y equals y sub 0 e to the 0.033t. I'm going to leave the 1 0 off, but I'm going to rewrite it here so we can look at it a little bit more clearly. Now the 3.3% is already given in this problem. It's right there. That's where the growth rate would go. But notice I didn't give you the y sub 0, but we can see it in the problem. The current population is 124. So I need to plug in that 124 for y sub 0. So I get 124e to the 0.033. And the other information I get here is that I want to know what the population is after 6 years. And so I'm going to enter the 6 in for time. And notice this problem really just becomes a calculation problem. So let's pull out our calculator, and we'll take a look at computing this. So again, 124. We're going to pull up our e. And again, I always like to use the one here that's above the natural log. So I hit second and raise to. And notice it does give me that parentheses. That's why I like it, because I need to do a calculation there in the exponent. 0.33 times 6. And I close that off. And I end up with 151.15. So it's approximately 151.15 is what I get from this calculation. Now let's take a look at the question. I want to find how many deer there would be in 6 years. So does 151.15 seem realistic? Can I have a partial deer in 6 years. So with a problem like this, it may make more sense to actually round to the nearest whole deer. And so the most reasonable answer for this problem would be 151 deer. So there are times where that decimal might be beneficial, but if you think about it logically, a full deer is probably more acceptable in this particular problem. All right, so let's extend this just a little bit. What if I ask you how long it would take for the population, or this deer population, to double in size? So I'm still talking about the same scenario here. Now, in the last video, we talked about what doubling referred to, so we're kind of bringing that back into play here. So again, I am looking at this particular scenario and this particular equation. So remember, my initial or current population is 124. If it doubles, what will my y value be? Well, it's twice 124, or 248. So 248 is equal to 124. E, growth rate hasn't changed, but notice I am looking for t here. I'm asking you for how long this is going to take. So I need to solve this equation. So again, I need to be focusing on the fact that I've got e raised to the variable exponent. So I'm going to start by getting rid of that 124 on both sides. And when I divide both sides, it should come as no surprise that this is 2, because after all, I doubled that to get the 248. So that will be common. Whenever you're doubling, you'd get a 2. If you were going to triple, this division should end up being a 3. So there is a relationship there. So 2 is equal to e to the 0.033t. Now, again, since I'm using the base e, I'm going to choose which log I'm going to use. I'm going to use the natural log. So I'm going to take the natural log of 2, and that's equal to the natural log of e to the 0.033t. And then at this point, remember our little rule that says that if I've got the natural log of e raised to an exponent, it always equals that exponent. So I get natural log of 2 is equal to 0.033t. Now it's a matter of just dividing both sides by 0.033. And in this particular case, if I go to compute it, again, more than likely it will be an approximation. So let's go ahead and do that. Natural log of 2, close off that parenthesis, divided by 0.033 is going to give me 21.00 if I rounded to 2 decimal places. But again, with this particular problem, it may seem more realistic to just say 21. And in this particular case, what was my length of time? Well, it's going to be in years. How do I know it is in years? Well, let's go up to the original problem for a second. The growth rate was given in terms of years, and so that's how I know what my label should be. So if it had said 3.3% per month, then my label would have been months, and I would have been a little bit worried about my deer population that was happening here. Would have been a deer explosion. So this is just another way of being able to apply logarithms and exponents into some problems that you will be running into in various other courses and in life. Now, the last thing I want to take a look at here is back up at the formula. Notice that I specifically was talking about a growth formula here, but I could also look at this as what we call a decay or depreciation formula. And in fact, I would not need to change this formula at all. The only thing that would be different would be K. When you're looking at a growth formula, then your K is always greater than 0. When you're looking at a depreciation formula, your K is less than 0. So if your constant is negative, that means you're decreasing in population, and you would have a decay or depreciation formula. If your K is greater than 0, as it was in this example, you can see that you actually increase. And so the formula ends up being the same. The difference is what value K is. So that's the second type of application problem I wanted you to be familiar with. You'll see some of these problems in your homework as well.